So in this lecture and in the next lecture, we shall look at some norm estimates for the Fourier transform. We shall prove that the Fourier transform maps L1 of R to L infinity of R. It maps L2 to L2. These are very important properties of the Fourier transform operator. So we know that if a function f is absolutely integrable, its Fourier transform exists. That is, if f is in L1 of R, then we know that the Fourier transform exists. What is the Fourier transform? F hat of chi equal to integral over R e to the power minus ix chi f of x dx. Take the absolute value. Take the absolute value mod f hat of chi less than or equal to, take the absolute value inside. So mod f hat of chi less than or equal to integral over R mod fx dx, because mod of e to the power ix chi is 1. That's the first thing that you see in the slide. So mod f hat of chi is dominated by integral over R mod fx dx. That is the L1 norm of f. In other words, the Fourier transform is bounded. It has an upper bound, namely the L1 norm of f. In other words, the L infinity norm of the Fourier transform is less than or equal to the L1 norm of f. Stated differently, the Fourier transform maps L1 into L infinity, and the norm estimate norm of f hat infinity less than or equal to norm f1. That estimate, the last displayed inequality that you see in the slide, indicates that this mapping is a continuous mapping. So this was easy, that the Fourier transform takes L1 to L infinity. Can we say something more about this? It turns out that L infinity is too big. The Fourier transform doesn't map it onto L infinity, it maps into L infinity. So let's see how to prove that. So let us look at a little more carefully. What can you say more about the Fourier transform? Can we say anything more? So first, let us prove the Riemann-Lebesgue lemma. We shall show that the Fourier transform decays to 0 as chi goes to infinity. This is the Riemann-Lebesgue lemma for the Fourier transform. Before we take the Riemann-Lebesgue lemma for Fourier transform, let us recall the Riemann-Lebesgue lemma for Fourier series that we have done right in the first module. Namely, if f is an L1 function, then integral a to b fx cos nx dx and integral a to b fx sin nx dx, they both tend to 0 as n tends to infinity. This was the Riemann-Lebesgue lemma for Fourier series. More generally, when f is L1 on a bounded interval a to b, the integral fx multiplied with cos nx or sin nx, that goes to 0 as n tends to infinity. Let us, for amusement, give a new proof of the Riemann-Lebesgue lemma for Fourier series itself. So let's go back to Fourier series and let's reprove Riemann-Lebesgue lemma by a totally different method. In fact, we shall look at Riemann's original proof of the important lemma that bears his name. Okay, so again I am stating the theorem just for convenience. If f is in L1 of minus pi to pi, then the Fourier coefficients of f decay to 0. Let us prove it first under the additional hypothesis that f is continuous. So f is a continuous function from minus pi to pi. What do? Extend f as a constant beyond pi and extend f as a constant beyond minus pi on the left. In other words, f of x equal to f of pi when x is bigger than or equal to pi, and f of x equal to f of minus pi when x is less than or equal to minus pi. So wherever draw the graph of the function and wherever it ends at pi and minus pi, just draw the horizontal lines starting at that point. So this extension now is uniformly continuous and bounded on the entire real line. So with this preparation, let us now prove the theorem. Let us call the integral I equals integral minus pi to pi fx sin nx dx. Let us do the following. Let us put x equal to y plus pi by n in the integral. So we are looking at I equal to integral minus pi to pi fx sin nx dx. We are putting x equal to y plus pi by n. So we get sine of ny plus pi. Sine of ny plus pi is minus sine y. Okay, so that's what happens. The minus sign comes out of the integral. Of course, the limits of integrations will change. It will go from minus pi by n to pi minus pi by n. That's what you see displayed in the slide. Now, let us add the two expressions for I that we have got. So we get 2I equal to integral minus pi to pi fx minus f of x plus pi by n sine nx dx. But you see, what has happened is that new transformed integral which goes from minus pi by n to pi minus pi by n, I write it as a sum of three integrals. One integral from minus pi to pi and the other are the remaining pieces. The two extra pieces that we got was I1 and I2, and the integral from minus pi to pi has been clubbed with the first expression. That's how you get the middle displayed equation in the slide. So what are these additional pieces I1 and I2? I1 is minus integral minus pi by n to minus pi f of y plus pi by n sine ny dy, and I2 is how much? Integral pi minus pi by n to pi f of y plus pi by n into sine ny dy. Okay. Now let us stare at this middle expression for 2I. You see, the first term integral minus pi to pi fx minus f of x plus pi by n. If I take the absolute value of that will be less than epsilon because f is uniformly continuous if n is large, and sine nx of course is bounded by 1. So first we shall look at what happens to I1 and I2. Let us first prove that I1 goes to 0 and I2 goes to 0 as n goes to infinity. That's easy. Why is that easy? F of x is uniformly continuous and bounded on the entire real line. So let us call capital M the bound for mod fx. So what happens to mod I1? Mod I1 less than or equal to integral over minus pi by n to minus pi mod f of y plus pi by n. Mod sine ny is bounded by 1 anyway, and mod f of y plus pi by n is less than or equal to m. So what do we get? It's m times pi by n. So mod I1 is less than or equal to m times pi by n, and that evidently goes to 0 as n tends to infinity. Similarly, we can show that mod I2 also goes to 0 as n goes to infinity. So we just have to worry about the first piece that you see in the middle of the slide. So now we have to look at this integral from minus pi to pi fx minus f of x plus pi by n sine nx. Take the absolute value inside the integral, it's minus pi to pi mod fx minus f of x plus pi by n dx. Appeal to uniform continuity, let epsilon greater than 0 be arbitrary. By uniform continuity, there is a delta greater than 0 such that when mod x minus y is less than delta, mod fx minus fy is less than epsilon by 2 pi. And we select the n naught so large that pi by n is less than delta for all n bigger than or equal to n naught. Then we replace mod fx minus f of x plus pi by n by epsilon by 2 pi if n is greater than or equal to n naught. So that's how you will get the entire integral will be less than 2 pi into epsilon by 2 pi, the 2 pi cancels out, you get that it's less than epsilon when n greater than or equal to n naught. In other words, I goes to 0 as n goes to infinity, and the proof of Riemann-Lebesgue lemma is over when f is a continuous function. Well, from continuous function to L1 function, the coast is clear. You have to apply Lusin's theorem. Lusin's theorem says that every L1 function be approximated by a continuous function in L1 norm. We already seen this in the first module, so I will not repeat it here. The essential part where a new idea was involved, I have spelled out in great detail. This is Riemann's own proof of the Riemann-Lebesgue lemma. Now let's go to the Riemann-Lebesgue lemma for Fourier transforms. What avatar does that take? It says that if f is in L1 of R, then f hat of chi tends to 0 as chi goes to plus or minus infinity. So let us imitate the same argument that we gave earlier. So to imitate the same argument, first let us assume that f is continuous on minus a to a. And let us prove that limit as chi tends to plus minus infinity, integral minus a to a fx e to the power minus ix chi dx equal to 0. Let's prove this first. Call the integral I as before, and again the same trick, x equal to y plus pi by chi, and proceed exactly as we did before. What is e to the power minus ix chi? Cos x chi plus I times sin x chi. Now I replaced x by y plus pi by chi. So sin x chi will become minus of sin y chi, because sin of pi plus theta is minus sin theta. Cos of pi plus theta is minus cos theta. So you'll pick up a minus sign exactly as we wanted. And then we should add the two expressions and get 2i. And we should proceed exactly as before, and we can finish the job. And that's a very good exercise for you. Now let us assume that f is in L1. Let epsilon greater than 0 be arbitrary. Select an a bigger than 0 such that the integral, the contribution of the integral outside minus aa is less than epsilon by 2. So outside the interval minus aa, the contribution is negligibly small. So we have to simply worry about what happens between minus a and a. Let's do that. So integral fx e to the power minus ix chi dx over r, absolute value less than or equal to, apply the triangle inequality, integral of the same expression outside minus aa plus integral of the same expression over minus aa. We get sum of two integrals. In the first one, take the absolute value inside and appeal to what I just said. Integral mod fx dx outside minus aa is less than epsilon by 2. That's exactly what you see in the slide. And fx e to the power minus ix chi dx integral is f hat of chi. So we get f hat of chi mod is less than or equal to epsilon by 2 plus mod integral fx e to the power minus ix chi dx from minus a to a. But we just proved that this goes to 0 as chi tends to plus minus infinity. So beyond a certain stage, this expression is less than epsilon by 2. That is, there exists a chi naught such that for all mod chi greater than chi naught, we have mod integral minus aa fx e to the power minus ix chi dx less than epsilon by 2. And so all in all, mod f hat of chi less than epsilon. And the proof is over. Now we would like to get the estimates for the Fourier transform in the L2 norm. Why do we need this? Because L2 of the real line is a Hilbert space. So the L2 norm has the pleasant feature that it makes L2 of R into a Hilbert space, and so the Hilbert space techniques are available. The argument, however, is not so straightforward. We have got to do a little more work. So what kind of work is required? The kind of work that is required is an analog of the Parseval formula for Fourier transform. In the context of Fourier transform, the Parseval formula is more popularly known as a Plancherel's theorem. So what is the Plancherel's theorem or Parseval formula, whichever way you wish to say it? Suppose f and g are the Schwarz class. You must recall what is in the Schwarz class. These are rapidly decreasing functions. Then integral minus infinity to infinity f of t gt bar dt equal to 1 upon 2 pi integral minus infinity to infinity f hat of chi g hat of chi bar d chi. Equation 4.11. This Parseval formula is extremely important in Fourier analysis. Numerous important theorems are based on the Parseval formula. We already seen how the Parseval formula implies the isoperimetric theorem in geometry. Likewise, this also has many interesting implications in harmonic analysis. To prove this theorem, we shall employ the e to the power minus epsilon chi squared trick. So let's see what happens. Let us try to do it directly and see where we get stuck. Once we understand where we get stuck, we also understand how to get around the difficulty, how to circumvent the problem. So let's start on the right hand side. RHS is what? It's the integral minus infinity to infinity f hat of chi g hat of chi bar. So, we must put in the expression for f hat of chi. What is it? Integral fx e to the power minus I chi x. We must put in the expression for g hat of chi, integral gy e to the power minus I chi y, but now we have to take the complex conjugate. So, that is why you get, all in all, you are going to get RHS equal to 3 integrals, an integral with respect to chi, an integral with respect to x, and an integral with respect to y. So, it is a triple integral. So, the outermost integral I am going to call with respect to d chi, integral with respect to d chi, integral over r squared fx gy bar e to the power minus I chi x minus y dx dy. Now, we shall try to exchange the order of integrations. So, the inner integral over r squared will become the outer integral, and the outer integral with respect to chi will now become the inner integral, but there is one small problem. What happens after you exchange the order of integration? The inner integral that you get finally reads integral over r e to the power minus I chi into x minus y d chi. This integral as it stands is meaningless. You must go back and look at the proof of the Fourier inversion theorem. We encountered exactly the same difficulty when we tried to prove the Fourier inversion theorem directly. And that is how we introduce the e to the power minus epsilon chi squared into the integrand. And here again, since the nature of the difficulty is exactly the same, the remedy is also the same, namely e to the power minus epsilon chi squared trick. Let us go ahead and do it. Now that we know what to do, let us try it out. Before we proceed, you have to recall the Fourier transform of the Gaussian. That I will leave it to you. I will not display it again. You go back and recall what is the formula for the Fourier transform of the Gaussian that will be used along the way. Okay, so start on the right hand side. What on the right hand side? Integral 1 upon 2 pi minus infinity to infinity f hat of chi g hat of chi bar. Now I throw in a e to the power minus epsilon chi squared d chi and allow the epsilon to go to 0. Now because f and g are rapidly decreasing, the limit as epsilon goes to 0 can go in or out of the integral as we please. The dominated convergence theorem applies. So I take the limit outside the integral and write it as limit as epsilon goes to 0 plus 1 upon 2 pi integral minus infinity to infinity f hat of chi g hat of chi bar e to the power minus epsilon chi squared d chi. That's the first line in the slide. Okay, now we express f hat as an integral and express g hat as an integral as we did in the last slide. And now we switch the order of the integrals as we did in the last slide. And finally, what do you get? The inner integral, instead of becoming a meaningless integral, is now a very meaningful integral. That's the beauty of this e to the power minus epsilon chi squared trick. So what do we get? Limit as epsilon goes to 0, 1 upon 2 pi integral over r squared fx gy bar dx dy and integral over r x pof minus I chi x minus y into x pof minus epsilon chi squared d chi. The innermost integral now in the second line is meaningful. Not only is it meaningful, we exactly know what it is. It is the Fourier transform of the Gaussian. And the Fourier transform of the Gaussian is another Gaussian. It will be root pi by root epsilon into e to the power minus x minus y squared upon 4 epsilon. We know the formula for the Fourier transform of the Gaussian. Let's use that formula, and we got root pi by root epsilon outside as a constant factor. So we get limit as epsilon goes to 0 plus 1 upon 2 root pi epsilon integral over r fx dx integral over r gy bar x pof minus x minus y the whole squared upon 4 epsilon dy. You see, we had 3 integrals, we had a triple integral, 1 over r squared, 1 over r. One of the integrals has been computed and we got a root pi by root epsilon factor. And that's how you got the third line in the displayed slide. Now, in the integral with respect to y, we make a change of variables. We put y equal to x plus 2 root epsilon z. So dy will be 2 root epsilon dz, and the 2 root epsilon cancels out. We are still left with 1 upon root pi. So we get limit as epsilon goes to 0, 1 upon root pi integral over r fx dx integral over r g of x plus 2 root epsilon z e to the power minus z squared dz. I can apply the dominated convergence theorem because f and g are rapidly decreasing. Take the limit inside the integral sign, you get g of x bar, which doesn't depend on z, it comes out. What is left over? Integral over r e to the power minus z squared dz, which is root pi, and the root pi cancels out, and we get RHS equal to LHS, and the proof is complete. And the Plancherel's theorem is completed. So in the Plancherel's theorem, let us take f equal to g. Let's go back to the Plancherel's theorem. If I take f equal to g in 4.11, what is the left hand side? The left hand side is the L2 norm of f squared. What is the right hand side? 1 upon 2 pi into L2 norm of f hat squared. So we immediately get, taking f equal to g, we get that if f is in the Schwarz class, if f is rapidly decreasing, then the L2 norm of f equals 1 upon root 2 pi into the L2 norm of f hat. Okay, let's display equation 4.12. Now it is this 4.12 that is extremely critical. It is this 4.12 that's going to enable us to extend the Fourier transform as an operator from L2 to L2. So that's theorem 43. The Fourier transform extends as a bounded linear operator on L2 of R, and further it's a linear isomorphism onto L2 of R. To prove this result, we shall use one small fact that the Schwarz space S is dense in L2 of R. We shall not prove this right now. If time permits, we could come back to this later, but for now let's just accept it that the Schwarz class S is dense in L2 of R. So now that we have established 4.12 for the Schwarz class, we must use an approximation argument and extend it from L2 to L2. Now as a map from S to S, the Fourier transform is a bijective mapping from S to S. Why is it bijective? The inversion theorem says it is surjective and it is injective. The inversion theorem says that this has an inverse. The Fourier transform as an operator from S to S has an inverse. Now let's go back and observe that if you take f and g, two functions of the Schwarz class, and take the Fourier transform of f minus Fourier transform of g, and take the L2 norm. So because I am thinking of the Fourier transform as an operator, I have to give it a name. Script f will denote the Fourier transform operator. So script f applied to f minus script f applied to g. Take the L2 norm, that's less than or equal to 1 upon root 2 pi L2 norm of f minus g. So this shows that the Fourier transform is uniformly continuous as a map from S to S, and the inverse is also uniformly continuous as a map from S to S. Uniformly continuous with respect to which metric? With respect to the L2 metric. Remember, S is a subset of L2, S is a dense subset of L2, and L2 has a norm and hence a metric. And with respect to this metric, both f and f inverse are uniformly continuous. Now we shall appeal to a theorem on metric spaces, a very general theorem on metric spaces, how to extend a function from a dense set to the whole space. So that's lemma 44. Suppose X is a complete metric space. What's a complete metric space? A metric space is said to be complete if every Cauchy sequence converges. L2 of R is a complete metric space. All the LP spaces are complete. So the completeness is extremely important. Suppose X is a complete metric space and Y is a dense subspace of X, and T is a mapping from Y to Y. And if T is uniformly continuous, then t extends continuously as a map from x to x. So now let us apply to the Fourier transform. What is our y? Our y is a Schwarz class. What is our x? It's going to be L2, and what is our t? Is going to be the Fourier transform operator. Alright, let's prove the lemma first. So let us take a point little x in our metric space capital X. Because capital Y is dense in capital X, x is a limit of a sequence yn of points of y. Okay, so now look at t of yn. Because t is uniformly continuous, this t of yn is going to be a Cauchy sequence. Yn is a convergent sequence, and so it is Cauchy. Thanks to uniform continuity of t, Tyn will now become Cauchy. And because x is complete, Tyn is going to have a limit. Call this limit Tx. This is all fine, but there is one small problem that we must address now. It could happen that you pick a point little x, there could be two different sequences, yn prime converging to x and yn double prime converging to x. Then we look at Tyn prime and Tyn double prime. Where is the guarantee that Tyn prime and Tyn double prime will have the same limit? They both converge for sure, but where is the guarantee that they have the same limit? In the slide, I have used a slightly different notation. Let's follow that notation. So suppose I got two different sequences yn and zn converging to x, and look at the corresponding sequences Tyn and Tzn. Then we have to show that Tyn and Tzn converge to the same limit, and so we are justified in calling this limit t of x. It's unambiguously defined. So to see this, let us take the two sequences yn and zn and interlace them, y1 z1, y2 z2, y3 z3. Because yn and zn both converge to x, the interlaced sequence also converges to x. Because the interlaced sequence is a convergent sequence, the corresponding sequence ty1, tz1, ty2, tz2, etc. is again Cauchy and hence converges. Because it converges, its subsequences will converge to the same limit, and so the subsequence Tyn and Tzn must have the same limit. That is exactly what we had asserted, and so Tx is unambiguously defined. And so we have extended the function t as a mapping from x to x. The continuity of this is an easy exercise, and I'll leave it to you to fix it. So now, equipped with this, we see that the Fourier transform extends as a continuous linear map from L2 of R onto itself, and it satisfies an estimate. The L2 norm of f is equal to 1 upon root 2 pi times the L2 norm of f hat. Equation 4.13 holds. So we have achieved the goal of extending the Fourier transform as an operator from L2 to L2. Well, there is this factor of 1 upon root 2 pi in 4.13, which is a little painful. Had that factor not been there, the Fourier transform would have been an isometry. It would have been a unitary transformation or a unitary operator from L2 to L2. But that 1 upon root 2 pi makes it slightly more complicated. It is not a unitary operator, but almost a unitary operator. So it is exactly for this reason that other books use conventions for Fourier transform in such a way that this 1 upon root 2 pi disappears from 4.13. But that's a matter of convention. But we would rather prefer our convention, which is used by PDE people, and we have to stick to this 1 upon root 2 pi in equation 4.13. So this completes the task of extending the Fourier transform as an operator from L2 to L2.